Welcome to Civil Engineering Edge. Today, we're diving into one of the most fascinating and essential areas of civil infrastructure, the design of bridges. Bridges are more than just structures that connect two points. They are masterpieces of engineering, combining strength, stability, and aesthetics to ensure safe and efficient movement across rivers, valleys, highways, and railways. But have you ever wondered what goes into designing such powerful and long-lasting structures? From the vehicles that pass over the deck to the foundations buried deep within the earth, every component of a bridge is engineered with precision. A well-designed bridge must withstand enormous loads, both static and dynamic, as well as environmental stresses like wind, earthquakes, and temperature changes. The safety of thousands of daily commuters depends on how well these components work together. In this video, we'll break down the entire bridge system into simple, understandable parts. We'll explore the superstructure, the substructure, and all their critical components, including deck slabs, bearings, piers, footpaths, and more. Each element plays a unique role in distributing forces, providing safety, and ensuring the bridge's longevity. Whether you're a student, an aspiring engineer, or just curious about how the world around you is built, this video is for you. Stay tuned and let's build some knowledge, brick by brick, beam by beam. 1. Introduction. Bridges are marvels of civil engineering that serve a vital purpose in our daily lives. Whether it's crossing a river, a valley, a highway, or a railway line, bridges provide uninterrupted connectivity, supporting the smooth movement of people, goods, and services. Their construction is not just about erecting a structure over an obstacle. It's a calculated process that involves science, design, and functionality. The design of a bridge must ensure that it can withstand a variety of forces: dead load, the bridge's own weight, live load, moving vehicles and pedestrians, wind forces, temperature variations, and even seismic loads in earthquake-prone regions. The structural components of a bridge must work harmoniously to provide strength, flexibility, and durability. Bridge design varies depending on its purpose, location, span length, and site conditions. A pedestrian footbridge will have vastly different structural demands compared to a multi-lane highway bridge. Materials such as reinforced concrete, press-dressed concrete, and structural steel are selected carefully based on these factors. In this video, we'll take you on a journey through the intricate world of bridge design. We will understand its two main structural divisions, superstructure and substructure, along with all essential components like deck slab, curbs, piers, foundations, and more. By the end of this video, you'll have a comprehensive understanding of what goes into designing and building a safe, efficient, and long-lasting bridge. 2. Components of a bridge. The design of a bridge can be broadly divided into two essential structural components: the superstructure and the substructure. Each plays a crucial role in the stability and functionality of the bridge. The superstructure comprises all elements above the bearings. It is responsible for supporting the deck slab, carrying live and dead loads, and transferring them through the bearings. It includes parts like the deck, girders, footpaths, handrails, and wearing coat. The substructure lies below the bearings and forms the load-transferring base of the bridge. It supports the superstructure and safely transfers loads to the ground. It consists of elements such as abutments, piers, wing walls, and foundations. The substructure's stability is vital for preventing settlement and ensuring long-term safety. Together, these two components form the backbone of any bridge structure. Proper coordination between them during the design stage ensures safety, strength, and serviceability. 2A. The superstructure. The superstructure is the upper portion of the bridge that begins above the bearings. It plays a direct role in supporting the dynamic and static loads placed upon the bridge. These loads include the weight of the structure itself, vehicles, pedestrians, and environmental forces like wind and temperature. Key components of the superstructure include the deck slab, main girders, cross girders, footpaths, parapets, handrails, bearings, and the wearing coat. The deck slab forms the roadway surface and is supported by girders that carry and transfer loads to the substructure. Footpaths and railings ensure safety for pedestrians, while the wearing coat protects the slab from surface damage and weather. The materials used in the superstructure vary depending on the span length, load requirements, and environmental conditions. Common materials include reinforced cement concrete (RCC), pre-stressed concrete, and structural steel. An efficiently designed superstructure ensures smooth traffic movement, distributes loads properly, and minimizes maintenance needs. Proper joint detailing, drainage design, and expansion allowances must also be considered in the design stage. The substructure. The substructure is the lower portion of the bridge that lies beneath the bearings. Its main function is to receive and safely transmit all loads from the superstructure to the underlying ground. A well-designed substructure ensures that the bridge remains stable and upright under all operating conditions. The substructure includes key elements such as abutments, wing walls, piers, and foundations. Abutments are located at the ends of the bridge and serve as vertical supports that also retain the approach embankment. Wing walls are extensions of the abutments that hold back the fill material and provide a smooth transition from road to bridge. Piers are vertical members that support the superstructure at intermediate points. The foundation is the part of the substructure in direct contact with the ground and is crucial to prevent uneven settlement or tilting. The type of foundation, whether shallow or deep, depends on soil bearing capacity, water table level, and load factors. The strength and reliability of a bridge are largely determined by how well its substructure is engineered. Any weakness in this section can compromise the entire structure. 3. Components of superstructure. The superstructure of a bridge is composed of multiple components that work together to provide strength, durability, and safe traffic movement. These elements are carefully designed and interconnected to handle the expected loads and environmental forces. The most prominent component is the deck slab, which forms the main surface of the bridge and bears the direct load from vehicles and pedestrians. Beneath the deck are main girders and cross girders, which provide structural support and transfer loads efficiently to the bearings. Next are the bearings, which are installed between the superstructure and substructure. They allow controlled movement due to expansion, contraction, vibrations, and seismic shifts. Proper functioning of bearings prevents cracks and stress accumulation in the bridge structure. On either side of the deck slab, we have curbs and footpaths. Curbs serve as raised edges to restrict vehicle movement and ensure safety, while footpaths offer a dedicated space for pedestrians. Handrails or parapets are installed along the edges for additional safety. Lastly, the wearing coat is a crucial protective layer applied above the deck slab. It prevents water ingress, resists wear and tear, and provides a smooth riding surface. Each of these components has unique functions but must work in harmony to ensure that the bridge remains structurally sound and user-safe. 3A. Deck SLAB. The deck slab is the uppermost component of the superstructure on which traffic moves directly. It acts as a roadway and is usually constructed from reinforced concrete, ensuring it has the tensile and compressive strength to carry both live and dead loads. The deck slab must be designed to accommodate various types of loads, including moving vehicles, pedestrians, and environmental forces like temperature changes and rainfall. Its thickness and reinforcement pattern depend on the span of the bridge, traffic intensity, and type of supporting girders. Waterproofing is essential to protect the reinforcement bars inside the slab from corrosion. Drainage spouts are also provided to prevent water accumulation, which could lead to surface degradation or leakage into the substructure. In modern bridge construction, precast deck slabs are commonly used. These are manufactured off-site, ensuring quality control, and are then installed quickly during bridge erection, reducing construction time and traffic disruption. A well-constructed deck slab is critical for the overall strength, durability, and functionality of the bridge. 3B. Curbs, footpaths, handrails, bearings, etc. A bridge's superstructure includes several minor yet critical components that contribute to safety, functionality, and user convenience. Curbs are raised edges provided along the deck to guide vehicle movement and prevent accidental slipping off the bridge. Made from concrete or steel, curbs absorb minor impacts and separate the vehicular area from the pedestrian zone. Footpaths are dedicated pedestrian walkways provided on either side of the bridge. They are usually constructed slightly raised from the main deck and fitted with drainage provisions to keep them dry and safe. Handrails or parapets are safety barriers placed along the outer edges of the footpaths. They prevent pedestrians from falling and enhance the visual appeal of the bridge. These are often made of metal or reinforced concrete and designed to withstand lateral loads. Bearings are highly specialized devices placed between the superstructure and substructure. They allow controlled translational and rotational movement due to temperature fluctuations, wind loads, and seismic activity. Types of bearings include elastomeric bearings, pot bearings, and rocker bearings. Together, these elements enhance the bridge's usability, protect its structure from damage, and ensure the safety of all users. Neglecting these details can compromise the performance and longevity of the bridge. 3C. Wearing coat. The wearing coat is the topmost protective layer laid over the bridge deck slab. It serves as the interface between vehicular traffic and the structural concrete deck. The primary function of the wearing coat is to safeguard the deck from mechanical abrasion, weather exposure, and water infiltration. This layer is generally made of bituminous concrete, though cement mortar or polymer-based materials can also be used. The typical thickness ranges from 25 millimeters to 75 millimeters, depending on the bridge's traffic load and design life. The wearing coat must be water-resistant, skid-proof, and durable enough to withstand the stresses of braking and tire friction. It should also have good bonding properties with the deck surface to prevent delamination. In addition to protection, the wearing coat enhances riding comfort and vehicle safety. Drainage provisions are integrated into the wearing coat design to allow quick runoff of rainwater, minimizing hydrostatic pressure and reducing the risk of skidding. Regular maintenance, inspection, and resurfacing of the wearing coat are crucial. If this layer deteriorates, it can expose the deck slab to moisture and chemical attack, leading to corrosion of reinforcement and structural weakening. 4. Components of substructure. The substructure of a bridge is its supporting backbone, located below the superstructure and designed to transfer all imposed loads to the foundation soil. It includes abutments positioned at the ends of the bridge. They support vertical loads and retain the approach embankments. Wing walls, extensions of abutments, they hold back soil at the bridge ends, guiding traffic smoothly. Piers, vertical columns that support the superstructure at intermediate spans for longer bridges. Foundations, base structures that transfer the entire load to the ground. These may be shallow foundations like isolated, combined, strip, or raft footings when the soil is strong near the surface. For deeper or weaker soils, deep foundations like piles, wells, or caissons are used. The choice of foundation depends on load intensity, soil bearing capacity, water table, and seismic conditions. A well-designed substructure ensures stability and prevents differential settlement. And that wraps up our journey into the design of bridges, from understanding the roles of superstructure and substructure to exploring the vital components like deck slabs, bearings, abutments, and foundations. Bridges may appear simple on the surface, but they are the result of intricate engineering and deep planning. Every element is carefully designed to work in harmony, ensuring durability, safety, and functionality for years to come. As we've seen, even components like curbs, handrails, and wearing coats play a huge role in both structural performance and user comfort. Understanding bridge design isn't just for engineers, it's for anyone who values the infrastructure that shapes our daily lives. With this knowledge, you're one step closer to seeing the world through the eyes of a civil engineer. If you found this video helpful, don't forget to like, subscribe, and hit the bell icon so you never miss our future videos. Let us know in the comments what civil engineering topic you want us to cover next. This is Civil Engineering Edge, and we'll see you in the next video, where learning builds the future.